it is now time to actually do an analysis. And we're going to find that a bell curve is going to emerge majestically from these ruins. Right. Now, keep in mind William Feller's exhortation. Even strong faith must be fortified by a statistical test. So we're going to try to come up with a principled mechanism to be able to analyze data like that presented. So let's go back. Here are Burt's 2 tables on intelligence from his 1961 paper. The first table, the IQs of adults. The second table, the IQs of their children. What is a principled path forward? Well, there are many kinds of tests one could imagine doing in this setting, but let's focus on one where we look at the totals in the last row of each table. The totals tell us something about the number of individuals tested in various IQ bins from, say, 50 all the way up through 140. Okay. The data themselves are scattered all over the place, but a cursory look at the last rows shows that there is a quite beautiful coherence of these numbers. The laws of large numbers appear to be working beautifully in our favor. So let me now show you a histogram plot of the last 2 rows, the totals for the IQs for the adults and for their children. Now, in the interest of explaining the mechanism for you, remember we are dealing with a nominal size of 1,000, though perhaps it's actually really 40,000, but it's been standardized to 1,000. And what I'm going to do and show you in this histogram table is to collect all the IQ bins to the left of 70, pool them together, and collect all the IQ bins to the right of 130 and pool them together. The motivation, of course, is that as you go down into very small IQs or very large IQs, that we have very few representatives. And it is well known that the very small probability occurrences have much, much worse confidence. But of course, this is in the interest of full disclosure, and the listener should judge for herself whether this is a reasonable procedure. T.W. Kerner has provided a very readable account of this entire saga, has pointed out that one of the reviewers of his book said that this was a subjective statistical fudge. But of course, the reader should make up her own mind as to whether this was a reasonable procedure. So what I've now done is collect the totals in the IQs for adults and children for you in various bins. The bins are IQs to the left of 70, and then 70 to 80, 80 to 90, 90 to 100, and so on, 120 to 130, and finally a last or 8th bin from 130 onwards, all accumulated together. Now look at the picture. This is very persuasive. The data themselves for adults and children were spread out. There were certain things you could glean from just the table of data itself. But the executive summaries, the totals, show a quite remarkable coherence. These numbers seem to march beautifully in lockstep. And we also say the emergence of a bell curve. It looks like this kind of data are beautifully explicable by a bell curve, a normal distribution. Remember, the data was standardized, centered at 100, with a spread or a standard deviation of 15. So to understand or compare it with a statistical posited generation mechanism, which is normal, which start with a hypothetical normal distribution, a normal density whose mean is exactly 100, whose standard deviation is 15, or equivalently, whose variance is 15 squared, or 225. Here is a posited normal distribution of IQs. Many biological processes have been posited to have normal approximations, in part because, presumably, of an idea that these processes like height, weight, intelligence, and other things perhaps could be thought of as being aggregates of very large numbers of independent perturbations, and then we wave our hands briskly and make a vague appeal to a central limit theorem, and voila, a normal density emerges. Howsoever it may be, here is a presupposed distribution which is provided as a potential explanation for the mechanism by which the data were generated. Now, what are the data? Well, we are sampling at random from this distribution. In other words, we create a random sample. Of what size? Well, naturally n, though here the nominal n we have in mind is n is a 1000. But bear in mind that the actual numbers reported, there's some uncertainty in that score. So this could actually be 40 times 1000 or 40,000 or some number in between. So n is some generic number, nominally 1000 in our application. We are going to generate a random sample honestly, transparently, by independent sampling from this bell curve with a mean 100, variance 225. Now, once you have a sample like that, what are we going to do with it? Well, we're thinking of IQs here as being measured on a continuum scale. But of course, when we report it, we bin the IQs into bins, traditionally in bins of size 10. So let's break up the IQ scale into bins, accumulate all the bins to the left of 70, and systematically put the other bins together, 10 at a time, and now we have 8 bins of IQ. Now here's what we do. Look at each element in the sample, x1, x2 through xn. Each of these values purportedly represents an IQ of a generic individual. That IQ is going to fall into one of these 8 bins. Accumulate the number of elements in the sample which were in the first bin. These were all the individuals in the sample whose IQ was less than a 70. Accumulate all the elements in the sample which fell in the second bin. These were the individuals in the sample whose IQs fell between 70 and 80. 80 and 90, and so forth. In other words, we binned the sample. Of course, if you do this, right, when you talk about accumulated numbers, our natural notation is to use S sub n. Our notation is going to get a little cumbrous, because now we have not one identity to take care of. For example, the number of successes. We have actually 8 bins. Let's keep n as a subscript, S for the number, and let's use as a superscript an identifier, 1, 2, 3 up till 8, which targets the bin that we're talking about. So Sn1 represents the number of outcomes in that random sample of size n, which fell in bin 1, IQ is less than 70. Sn2 with the number of outcomes in that random sample, which fell into the second bin, in IQs between 70 and 80, and so on down, with Sn8, all the outcomes in the accumulated bins from 130 on to the right. Okay. Modestly more complex notation, but not grievously so, I hope. Right? S sub n we are familiar with. It's an accumulated sum, a total, and the superscript tells us which bin we are talking about. So Snk represents the number of elements in the sample which fell into the kth IQ bin. Let's promptly generate these numbers, and I'm going to show you a particular sample that I generated with n equal to 1000. So we have the adult IQ numbers, the children IQ numbers next to them, and flanking them as a third column, a third bar, the number of elements in a random sample of 1000 from a normal density with mean 100 and variance 225, the number in each of the 8 bins, Sn1, Sn2 through Sn8. Of course, the sum of these Sns is exactly 1000. There are 1000 elements in the sample distributed in these numbers in the 8 bins. Again, a look at this shows that there's a quite remarkable consistency between these numbers that I actually obtained in one particular sample that I generated and the numbers provided by Burt in his tables. And they all look like there's a very good potential for a normal fit. The bar to the right is from a normal distribution. The other 2 bars are potentially from a projected normal distribution, but that is what we are testing. If anything, the data I generated appear to be a little bit more variable. The data that Burt provided appears to be much more convincing. but they're all very close and they all seem to have a reasonable normal fit. So here's a question now. To do an analysis, in the counts of the number of elements in the sample in each bin, of course these are chance driven. How are they distributed? So now let's take stock again. Let's go back to our picture. Do you remember? We are dealing with a hypothetical normal distribution of IQs with a mean 100, variance 225, or equivalently, standard deviation is 15. We are going to generate a random sample by independent sampling from this distribution, and we are going to put the sample into 8 bins of IQ. What is the chance that a given element in the sample falls into the first bin? What is the chance it falls into the second bin? What is the chance it falls into the third bin, and so on? Well, the probability that a number drawn at random from this normal density falls in a given bin is, by our usual procedure, the area under the curve of the density for that bin. And now all we've got to do is a simple numerical computation which any internet calculator will do for you for what these areas are. And I'm going to give you a tabulation of these areas. So this is a numerical estimate of the area under the curve in each of these 8 bins. Remember, we have 8 IQ bins. Bin 1 is IQs less than 70. Bin 8 is IQs bigger than 130. The other bins are IQ bins of width 10. A typical IQ bin, let's say, is J. J runs from 1 through 8. What is the chance that a random sample member falls in bin J? Naturally, let's call it little p sub j. And the numbers little p sub j are clearly symmetric around the center, and they increase from 0.0 to 8, truncated to 4 decimal places, all the way up to 0.2475, and then decrease symmetrically on the other side. Now, with this in place, what can we say about the distribution of the number of elements in each of these 8 bins? Well, let's take a look at the first bin. You've got a sample, and a certain number fall into the first bin. The chance of falling into the first bin is P1. We have repeated independent trials in the sample, and each sample member independently has a chance P1 of falling into the first bin. The number that fall into the first bin, naturally, is the accumulated sum of these trials. Think of a trial as having a success if it falls in the first bin. Success probability is P1, failure if it falls in any of the other bins. The accumulated number of successes in our old notation is Sn1. And now we see that it must be a binomial distribution corresponding to n trials with a success probability of P1. Likewise, how many fall into the second bin? Well, each trial has got a chance P2 of falling into the second bin. There are n independent trials. Sn2 is binomially distributed with parameters n and probability of success or bias P2. And likewise, all the other SNKs fall into place. Each of these is binomially distributed, corresponding to n trials with varying success probabilities based upon the area under that normal curve. Remember the Moivre's theorem, Laplace's theorem. A central limit theorem beckons. A normal law beckons for these sums. And the normal laws are going to be centered where? Well, Sn1 has expectation n times P1. Sn2 has expectation n times P2, and so on. Let's take a look once more at the histogram of values, this time with a 4th column, the expected values for these numbers Snj. The expected value of Sn1 is np1, expected value of Sn2 is np2, and so on. And again, we see a quite remarkable concordance of these values. The values reported are accumulating near their expected values. There seems to be a concentration, a drift in that direction. The law of large numbers, the central limit theorem. Our question now is, well, how do these values actually compare with what we expect? Can we quantify this? This will be the basis of a principled statistical test.